The electric field due to a line of charge. So consider a circular ring having continuous charge, positive charge on it, and we're going to find an electric field at point P at a distance z from the center of the ring. And notice that we've considered a small amount of length, the differential length, and also a small amount of charge, the differential charge. Notice that the differential charge equals to the linear charge density times the differential charge equals to the linear charge density times the differential length. So we're going to find electric field, and we'll write the same old expression, but instead of Q we write differential of Q because we're finding it for a small portion, and then we'll integrate that. So notice that I've replaced dq by lambda ds, and then r squared by z squared plus capital R squared. That's because of a little geometry. So this here is the right angle triangle, and this is the longest side, and the square of this side is equal to the sum of these two sides. So I've written that instead of r squared, and notice that the cosine of theta, I've written cosine of theta. So the cosine of theta is equal to the adjacent side z divided by the longest side, the hypotenuse. Now you might be wondering, where does this cosine of theta come from? Consider a point charge here. So this charge has two components, a parallel and perpendicular. So the parallel component is in the positive y direction, and the perpendicular component is in this, to the right axis. And similarly, a point charge right here has the perpendicular component opposite to the first one right here. So the perpendicular component cancels, and we're left with the parallel component. So we're gonna add those up, and that's where the cosine of theta comes from. So in order to add them up all, we take the integral starting from 0 point right here to the 2 pi r being the length of the circumference of the ring. So the electric field then becomes this expression is the value of the electric field, and cosine of theta equal to z divided by r, and the value of r equals to under square root of z squared plus r squared. So we multiply this, and notice that I've taken all the terms out of the integral because these are constants. They don't change. The only thing that changes is the length, the differential length. So we're going to integrate those, and we're left with this expression. Notice that there's a linear charge density lambda and the length 2 pi r, and the length times the linear charge density equals to the charge. In this case, it's the total charge. So we're left with this expression, and this is the expression we use to find the electric field due to a line of charge. Now here's the magical part. If we put r equals 0, if we reduce this radius to 0, then we're left with the same old expression that we used to find electric field for a point charge, k, q over z squared, k being the constant, which is equal to 1 over 4 pi epsilon naught. All right, thanks so much for watching.